morning. So, today I will continue this lithium ion battery, and what we have discussed in the previous lecture is that we have just seen what is the the basic construction of lithium ion battery, what is the importance of lithium ion battery, what is the working principle of lithium ion battery, and why we need such storage devices. And also I introduced different materials used in lithium ion battery, because we know that lithium ion battery basically consists of 4 components: a cathode, a anode, electrolyte and a separator. Okay? And it works on the principle of charging and discharging electrochemical reactions. So, I will continue the material aspects of lithium ion battery, but let us just see once again that what we have discussed and how this lithium ion battery works, taking a particular example of a particular cathode and an anode material. So, as I mentioned in the previous class, you can see that we have to get the energy levels, different energy levels of a lithium ion battery. And if we look at different energy levels of a lithium ion battery, then we have, this is corresponding to the potential of anode, this is mu c is for the cathode, okay. And then in between anode and cathode there is electrolyte, and these are 2 levels of electrolyte, one is LUMO and another is HOMO. And we already know what are LUMO and HOMO stands for and what is these 2 energy levels. So, now if we look at the open circuit voltage, the way we define open circuit voltage is that the difference between the electrochemical potential of anode and cathode, that is called open circuit voltage or VOC. Okay. So, when we place cathode and anode and electrolyte and separator and make a lithium ion battery which is like this. Okay. So, we know that it works on the principle of intercalation and de-intercalation of lithium in different electrodes, that means in cathode and anode. So, as I discussed in the previous class, there are 2 processes which are going on continuously in a lithium ion battery. One is, say, the discharge process, okay, where you can see the lithium goes from anode to cathode in the discharge process, and electron moves in this direction, okay. And it is a de-intercalation process. That means, if I have an anode which we discussed, say one typical is graphite, then lithium which are intercalated inside the graphite layers gets de-intercalated during discharge process and move towards cathode. And here one typical example of cathode which we have considered is LiCoO2 or LCO, this is as cathode. Okay. So, now once the lithium travels towards a cathode, then it gets intercalated in the cathode material, and then we have to apply an outside power source. We have to plug it in a in any socket as we do for batteries. So, here you can see the lithium moves from cathode to anode, electron moves in this direction and charging takes place. Okay. So, during charging we charge the lithium ion battery by the process of de-intercalation of lithium from cathode to anode, okay, which moves towards anode. after deintercalation from cathode. All right, and then when we do discharge, we connect a load across the two electrode, and whatever load we connect, it is basically the power is delivered to that particular load. Okay. This is the way it works. So, typically the reaction which happens are, let me write down the reactions. So, LiCO2, which is cathode, it becomes Li 1 minus X CO2 plus X Li plus X E minus. Okay. So, now this the anode which gets now lithium which is actually now is getting intercalated in the anode, say like graphite. So, if I just like the 6 carbon atoms, something like 6C, then lithium reacts with it and it produces LiC6. Okay. So, now if I add these two reactions, so we can write it like LiCO2, basically it becomes Li 1 minus X CO2 and then it produces LiC6. Okay. So, shuttling of lithium between cathode and anode take place due to intercalation and deintercalation process. So, now coming back to again to the material aspect. So, as I mentioned, one of the cathode material is LCO, but in the previous lecture I told you that the problem with LCO material, cathode material, although it was just after its discovery, it was immediately commercially applied in the device by Sony and it became very popular, the LCO as a cathode material. But people slowly realized that there are two problems with LCO to use it as a cathode material. One is the cobalt is costly, okay, this is a transition metal, and then second is because of exothermic process oxygen gets released from this particular structure. Okay. So, what people started thinking that can we just start the combining a different transition metal and make a slightly modified cathode material. So, one particular choice is Li. So, people talk about a combination of nickel, manganese and O2. This is one choice and this is known as popularly known as NMO cathode material. Okay. So, here we just get rid of cobalt and put instead of cobalt we use nickel and manganese as transition metal for the cathode material. People also later realized that let us have this cobalt also inside this structure. So, one can have nickel X, cobalt Y and manganese Z O2. This is known as popularly known as NCM cathode material. And this became very popular cathode material when people found it in one particular composition where lithium nickel around 0.33, cobalt also around 0.33, manganese also 0.33 and oxygen. This is a particular composition of NCM where people found it very good because it gives very good the energy density of a lithium ion battery. Okay. So, if we just look at these three materials and compare their performance in different the physical properties point of view and look at that how the different element or transition metal element and is in which property they are better. So, if I consider or what is the parameter that they are good at. So, if I consider say chemical stability and consider these 3 transition metal, then one can find that in terms of chemical stability, manganese is better than nickel, which is better than cobalt. Okay. So, now second thing, if we consider structural stability, in this case cobalt is better than nickel and which is better than manganese. Okay. If we consider electrical conductivity, then again cobalt is better than nickel, which is better than manganese. If we consider abundance, then manganese is best, it is nickel is next, followed by cobalt. And then if you consider the environmental benignity, then again manganese is best, followed by nickel and then cobalt. So, it is important because when we design a material for a particular the purpose, here it is for the cathode material, we have to see all these parameters, and therefore, a good combination of nickel, cobalt and manganese can make a very good the cathode material for lithium ion battery. Okay. So, another aspect which I mentioned, and again I repeat, that when people use the LCO material as a cathode material, they also found that in order to improve the stability of LCO material, one can coat oxide like aluminum oxide, titanium dioxide, strontium oxide, etc., to have a better stability. Okay. And then next is how to use different combination of transition metals in a particular cathode structure. All right. So, apart from these, as I mentioned that there are other cathode materials also which are popular, and I mentioned that it is Goodenoug's team of researchers who worked together and found different material. Another material is spinel oxide. So, one typical example is LiMn2O4. Okay. Then other materials are polyanion, that is also I discussed. One typical example is LiFePO4, or this is also popularly known as LFP material, or LiMnPO4, this is known as LMP material. These are all materials for cathode. Okay. So, the polyanion material is specific the purpose, it apart from giving a high voltage output, they are also extremely stable because of their typical structure. Many other materials are also under investigation, and you can find it in the literature what material people are recently using for lithium ion battery, or what materials are under research in lithium ion battery. Okay. So, one important aspect in cathode material or in anode material is intercalation of lithium and the transport of lithium. Lithium has to go inside that material and then it has to be conducted also. So, one typical feature you can see here, like in this 2D structure of say LiMO2, where M stands for any transition material. In this case, the lithium moves from one octahedral site to another octahedral site through a vacant tetrahedral site. And in 3-dimensional, in spinel oxide, you will find that it is just opposite, that lithium moves from one tetrahedral site to another tetrahedral site through a vacant octahedral site. Okay. So, one needs to know two important things. One is the material intercalation probability inside the cathode as well as in the anode, and then how it gets transported through this material. Okay. So, one can find detailed about this in the literature. I am not going to discuss in detail about that. Let us just look at what are the other the anode material that people use in the lithium ion battery and that you find in the literature. So, I already discussed about graphite as a anode material, and I have also shown you a picture where this lithium, the atoms get intercalated inside the graphite sheet, okay, and then during discharge they get deintercalated from the graphite sheet and move towards the cathode. And then I also discussed how this the voltage versus discharge capacitance characteristics look like. Okay. So, it is not only graphite, many other carbon materials also which have been chosen as one of the the materials, best materials for anode of a lithium ion battery. If I consider graphite, we all know this is a layered structure. Okay. So, the intercalation probability is high, lithium transport is also very good. Moreover, this is abundant, carbon materials are always abundant, they are having a good mechanical stability. So, and also one can achieve almost theoretical the energy density if we use graphite. However, there are certain problem because we have electrolyte also in this lithium ion battery. So, it happens sometimes that it eventually exfoliates the graphite, and once it takes place then the capacity decreases. Okay. So, eventually the energy density also decreases. So, people thought about some alternate materials as anode material. One popular material, alternate material is conversion type anode material or CTAM, which are also used in as anode material. So, what are the typical examples? Typical examples are say magnetite or Fe3O4 and pyrite, FeS2, pyrolusite, MnO2, etc. These are all typical examples of CTAM. Apart from that, people also have studied sulphide, okay, like MoS2 or carbide, okay, nitride as anode material for lithium ion battery. So, what are the advantages of using these particular materials as anode material in the lithium ion battery? They are non-toxic. This is a very important thing because the material should be always environment friendly. They also shows high power density. This is one of the goal of any battery like lithium ion battery, and they could achieve the theoretical specific capacity. They are also abundant in nature. All these material like magnetite, pyrite, etc., they are all found in nature. So, they are abundant in nature and also they have a low cost fabrication process. Okay. And from the theoretical model, people have almost predicted about 926 milliampere hour per gram theoretical capacity of this type of anode material when these anode materials are used in lithium ion battery. However, there are some disadvantage of these materials also. There are some rapid the decrease in the capacity which is seen, and also the cycling stability is also not up to the mark, and then electron conductivity is also not very good in this material and poor rate performance. So, there are certain disadvantages of this material, advantages of this material, there are certain advantages of carbon based material and some disadvantage of carbon based material. So, once the one start designing a device of lithium ion battery, one is to take care of all these important points, advantages and disadvantages, and for a specific design of a specific energy density or specific capacity, one is to see what is the most optimum material for a particular lithium ion battery. Okay. In literature, people have also shown some intermetallic compound. I am just mentioning one particular reaction here, like the different intercalation process which can take place. Like you see this Mg2Si, it takes up lithium electron, it becomes LiX Mg2Si. Eventually, it again intercalates lithium and it forms a Li critical Mg2Si, okay, which is an intermediate compound or not a very stable compound, and then it becomes Li saturated Mg2Si lithium silicon alloy, and then this Mg again intercalates lithium and electron and forms an LiMg alloy. So, these type of complex materials are also nowadays people are studying as anode material for lithium ion battery, and one can find several examples in the literature. Okay. So, broadly if I just summarize it, what I discussed with you now is that what are the possible cathode material of a lithium ion battery and what are the anode materials for lithium ion battery, okay, and how these the materials work. Okay. So, whatever materials so far I talked about, they are all bulk material, okay, or the material which consists of micron sized particle of a particular element or the combination of element. So, now the question is, if we reduce the dimension, is it important, okay, to reduce the dimension? In most of the cases, whatever the devices so far we have discussed, okay, of different energy materials I have discussed in previous lectures, almost all the times I also touched or discussed about the nano phase of this material, and here also we will see the nano phase has a typical advantage to use it in the lithium ion battery. So, what are the typical advantages of using a nanostructured material or nanostructured cathode and anode material for lithium ion battery? So, broadly if we look at the advantages of using a nanostructured material or nano phase material for anode and cathode material are, one can have a new reaction. Okay. You can also get some sort of new reactions which is not possible with the bulk material, and then one can have a larger electrode electrolyte contact area. This is very important thing, because that when we increase the surface area, when we have a large number of atoms present, okay, we can have a better electrochemical reaction, and if we have a better electrochemical reaction, we have a better performance of the device. Another important thing is the short path length for both electronic and ionic conduction. Ionic conduction here is the lithium ion conduction. So, this is a very important thing. So, let me just tell you that when we talk about materials of any electrode, we basically we look at three important things. One is the crystal structure of this material that I have already shown, and another is some physical properties of this material, like its specific capacity, like its mechanical stability, its thermal stability, etc., and some chemical properties of the materials, okay, like the intercalation probability, like reversibility, etc. So, now the question is, we have not really looked at from the point of view to reduce the size of those materials. Okay. That means that if I come from micron size material to nano size material, what are the advantages that one can see, and that actually is directly related to short path length. What is the reason for that? Because that when lithium gets intercalated in any material, suppose in any anode material or any cathode material, it actually diffuses through that material. So, I just now I showed that lithium movement from one octahedral site to another octahedral site through a vacancy, okay, in a tetrahedral site. So, that means it is a diffusion process. So, the diffusion process is basically decided by two important quantities or parameter. One is diffusion length of lithium. So, I can write LLI, which is diffusion length. Another is DLI, which is diffusion coefficient. Okay. So, this is important. We need a higher diffusion coefficient inside the material, and what people have seen that what so far the materials I have discussed, that bulk material or the material where the particle size are of the order of few microns to few hundred micron, the diffusion coefficient is quite low. You can take typically an example of say titanium dioxide. If you take a bulk titanium dioxide and look at the diffusion coefficient of bulk of lithium in bulk titanium dioxide, it is much lower as compared to if you have a nanoparticulated titanium dioxide. That means your particle size are of the order of few tens of nanometer, then you have a much higher or better diffusion in that particle, okay, in that system. So, therefore, apart from crystal structure, physical properties and chemical properties, the size of the particle and shape of the particle is also important. I will come back to this one just after this discussion. So, how really these different size and shape actually work in a different manner or in a better way for as a cathode and anode material. But overall we can tell that the short path length for both electronic and lithium ion transport is very important for a nanophase material, and also people have seen higher lithium storage capacity for nanoparticles because you have again the large surface area. So, you all know the surface to volume ratio enhances much when you go from the bulk material to nanophase material, and that also increases the capability of lithium storage and higher electrochemical activity. That is also related to the number of atoms which are present in a particular area. Okay. If it is more, then definitely the electrochemical activity is better. So, we have several advantages when we go from bulk phase or micron phase to nano phase material for lithium ion battery, cathode and anode. So, if you look at that how these nanoparticulate systems look like. So, you can see a very nice demonstration here. So, you can see these are all small nanoparticles and these are the current collector. So, this is a material on which, so you can see this is a typical anode material or say a cathode material which are nanophase material. So, you have nanoparticle and there are some small recombination sites here, okay, and these are bare nanoparticles. Bare nanoparticles means you have not coated anything in the nanoparticle. So, I told you just now that the transfer or the transport of lithium is efficient, okay, in that particle when we compare it with micron size particle. But there is some issue with this particle. The issue is that when I consider the bare particle, the issue is that there is a random motion or kind of a random walk of say electron in that particular nanoparticulated system. Okay. So, that random motion sometimes leads to scattering and it cannot, the electronic conductivity becomes less and it cannot reach to the collector, okay, and therefore, you can have a very low current density. There is a possibility. So, one needs to take care of this, and one way to take care of this is what people showed, that one can have some blend here, okay, carbon blend. So, some particles you put in a carbon blend. So, therefore, electron gets a path in that blend, or one can also coat like carbon coating of the nanoparticle. That is also possible. Chemically one can coat this nanoparticle with some carbon, and therefore, this carbon coated nanoparticle gives a better electronic transport. Okay. So, this is one way. The point, if you remember that we always highlight this point, that we need a better the surface or higher specific surface or surface to volume ratio should be higher, and therefore, nanoparticulate systems are the best for this. Okay. But then we need to redesign it little bit like with carbon coating or blending to have a better electronic transport. If we do not do that, then we change the shape of this nanostructure. So, what shape one can have? One can have a shape like nanotube, nano wire, nanorod, etc. So, they are all cylindrical shape or one dimensional shape of the nanoparticle of the nanostructure, where nanoparticle is, one can say, 0 dimensional shape, and you can see that one can have the nanorod which are randomly on the current collector, or one can have nanorod which are vertically grown on the current collector. Okay. So, what are the advantages one can have once you make a vertically grown structure or nanorod kind of structure? One can have a easy path of conduction. Okay. This is extremely important. For the nanorod, there is an easy path for conduction or directional path. Okay, so in the nanoparticle system, which we have seen, we have just now I have shown that it's a kind of a random motion. This is now the problem is solved when you have a nanorod kind of structure or nano-wire kind of structure, when there is a the motion which is directional. Okay. So, people do lot of the playing with the morphology of cathode and anode, and some of the typical morphologies that we will see later. But if I just consider a nano-wire kind of structure and a nanoparticle kind of structure, what advantage we get? So, you can see when we plot capacity with respect to cycle number for different the structure. One is silicon nanowire and silicon nanocrystal. So, if we consider the charging in those cases, you can see this is for the silicon nanocrystal SiNC, and this is for graphite charging, this is for graphite. And now, if we consider silicon nanowire, we have much higher capacity for similar cycle number. Okay. In fact, people have also shown that this capacity can be retained for different cycles. It starts with a very high capacity. So, you can see the capacity here is almost close to 4000 or higher than 4000. It reduces little bit and it comes in between 3000 to 4000 after some cycle, and then after 2 cycles in fact, and then it becomes almost stable. Okay, for silicon nanowire. But now we go to silicon nanocrystal, it is drastically reduced. The capacity is only close to 1000. If we have graphite, then it is even lower. So, that means we get a gain of almost 3 times capacity when we use from silicon nanocrystal to silicon nanowire, and as compared to graphite. Okay. So, this is extremely important point, and now you can get a direct comparison between nanowire and nanoparticle for TiO2, and if you again plot his specific discharge capacity, then you can see this is much higher for nanowire, it is much higher as compared to TiO2 nanoparticle, and this is also stable with cycle number up to 100 cycle number it has been plotted. It is stable with retaining a high capacity value. Okay. So, I gave enough justification why we require a nano phase material, and then different morphology of nano phase like nanoparticle and nano wire. Now, people have also worked with different structure, some core shell kind of structure, some hollow core, okay, where we have a different level of volume expansion, which CO3O4 coated by nickel oxide. So, this hollow core you can have a more volume expansion. So, you have more lithium intercalation probability, and now if you make a coating on top of it, you can have a better mechanical stability also. So, you can see again capacity plotted versus cycle number. This is for hollow sphere, the red one is for solid sphere, and the other one is for triangle one is the for the nanoparticle. So, definitely you have higher capacity for hollow sphere as well as for solid sphere as compared to nanoparticle. Okay. So, apart from that also people also do little more nano designing, nanoscale designing of the cathode material. One beautiful nanoscale designing is the branched nanostructure. So, you can see, so this is a typical branched nanostructure, a typical branched nanostructure. Okay. And this branch nanostructure contains different nanostructure in that. So, the branches could be the nanowire and nanorod shape of branches, and inside that there could be a hollow sphere, or there could be the core shell kind of structure. Okay. So, it makes a material designing a little more complicated, but you can have the advantages of different nanostructure, including very high surface area. Okay. So, therefore, you have a very high electrochemical reactivity when one consider the branch nanostructure as the material for electrode. Okay. So, now let me make a comparison between different nanostructure when we consider anode material. So, let me just give you this show you this table. So, you can have this SNO2 hollow nanostructure, where this is the typical size 100 to 250 nanometer, and this is the specific capacity. Okay. So, if we consider it SNO2 hollow nanotube, and this is the typical size, and then there is a reduction in specific capacity, and now you come to mesoporous SNO2, where this is the typical size and you have less specific capacity. Okay. Now, come to SNO2 nanorods, you have this is the typical diameter, this is the typical length, 60 nanometer diameter and 670 nanometer length. You have slightly different or slightly higher specific capacity. Similarly, when you have SNO2 nanowire, you have slightly higher specific capacity, and then SNO2 coated with carbon hollow nanosphere, you have slightly different specific capacity. Okay. So, these are typical examples of different morphologies of SNO2 which people have reported and different literature. So, these are some more example like cobalt metal coated SNO2 nanoparticle. So, you have a slightly higher specific capacity, again SNO2 nanowire covered with SN nanoparticle, you have slightly higher the specific capacity, but you have nano sized rutile TiO2 less specific capacity. Okay. So, TiO2 carbon combination, TiO2 graphene nanocomposite with different specific capacity. So, what it means that whatever specific capacity you design for, okay, you look at its particular or specific morphology of the material or the nanostructured material or nanostructured electrode, here it is cathode, anode, and then you design it accordingly. Okay. Fine. So, these are all about the nanostructured anode, and similarly you can have different nanostructured cathode, and I am not going to discuss in detail about cathode because the physical processes are same. It is again the same intercalation followed by diffusion of lithium, electronic conductivity, ionic conductivity, etc., mechanical stability. These are all the the parameters which one need to look into, and these are few the morphologies which one can find in case of cathode material also. So, there are different nanomorphologies, and then if I just compare the morphologies, say nanorods. So, this is typical the capacity with this typical voltage which is quite high 4.5 volt, and then if we come to same nanorods at it depends how what material you have grown. We have a little different specific capacity. Nanoplates, we have different specific capacity with different voltage. Nanospheres, different specific capacity with different voltage. Okay. Nanoparticles with we can see a less specific capacity, however the voltage remaining almost same. Okay. So, different people have reported in different literature, and one can find out the literature in a review which I have shown here, and one can see how by varying the different morphology of the nanostructure one can design cathode material also like anode material for different specific capacity and different voltage. So, overall that we get a very good idea about how the the different morphologies or nanostructure can influence the basic properties of a lithium ion battery and can be used for designing a device for a particular purpose. Okay. So, now we come to the third component. So, I discussed about cathode, I discussed about anode, and I also discussed about these different phases of that of this electrode material. And now, let us look at the another component, that is electrolyte. So, electrolyte, you can understand what is the role of electrolyte. The role of electrolyte is that when lithium is released from say anode and it is going towards cathode, or lithium is released from anode and it is going towards cathode, it cross across a separator and they are inserted in the electrolyte medium. Okay. So, therefore, there should be a very good transport of lithium from one electrode to another electrode. So, one can say the shuttling of lithium between the electrode should be good enough or should be proper when we consider the medium which is in electrolyte. So, what are the essential properties of an electrolyte? It should be a good ionic conductor and electronic insulator. Second, it should have a wide electrochemical window. Okay. So, what is the meaning of wide electrochemical window? Wide electrochemical window means suppose we operate it for 2 volt, it depends. I mentioned you that if we change the cathode material, then voltage becomes 2 volt, and if we use another cathode material say from sulphide to oxide or spinel oxide or polyanion, then immediately the voltage increases. So, 3 to 4 volt. Okay. So, electrolyte should be the capable enough to work for this large the voltage range. So, therefore, it should have a good electrochemical window and it should be inert to all other components. What is the meaning of that? Inert in that sense is that we have various other components which is here, like separator is a material, the substrate where we have grown the cathode and anode material. Okay. The electrolyte should not corrode this in a simple sentence I can say, or should not destroy the different materials used in the lithium ion battery. This is a very important point. It should be thermally stable. What does it mean? It means that its melting point, boiling point, etc., should be at the value should be such that it is not disturbed in the working temperature regime. It may be room temperature, it may be another temperature regime, but it should not get disturbed with the temperature. And it should also have low toxicity, that is also very important, because electrolyte can always be problematic because of the toxicity issue, and there is a safety issue always. I will come back to this point also, and it should be more environment friendly, and then finally, it should have a lower cost. So, these are typical properties of electrolyte which we should look for when we design a lithium ion battery with anode, cathode and an electrolyte. So, if I just make a different kind of electrolytes. So, in LIB generally the electrolytes which are used are non-aqueous electrolytes. Aqueous electrolyte, okay. One can also use ionic electrolyte, One can also use a polymer electrolyte with say either polymer gel or polymer in solid or a kind of hybrid electrolyte. These are all different electrolytes which people have studied in different lithium ion batteries, okay, and designed different lithium ion batteries with different electrolyte. So, what is a electrolyte? If we just look at in a very basic fundamental way, it is basically a lithium salt, lithium based salt. If I consider as a a non aqueous electrolyte, it is dissolved in some organic the liquid, okay. All right. So, one can have a very good the conductivity of lithium, as well as one can have a very high specific energy when one uses a non aqueous electrolyte. But the problem with this is that they are flammable, okay, and therefore, there is a safety issue. So, people started using aqueous electrolyte, like you dissolve the salt in water instead of in any other the organic fluid, okay, which is the flammable. So, if you take an aqueous, so that problem is solved, you do not have the problem of flammable, but the transport of lithium is not that good. You also have to compromise with the specific energy or the capacity of the battery. So, now what people try to look at it, one can have a ionic electrolyte, a combination of an ionic material and aqueous and non-aqueous solution. One can mix a combination and get a different transfer of lithium with a different electronic and ionic conductivity. That is also been explored, but they found eventually that in this case the viscosity becomes high and eventually the ionic conductivity decreases. Okay. So, there are again some safety issues with this type of electrolyte. So, people also explore the polymer electrolyte, gel type polymer or the solid state polymer, which are extremely stable, okay, and they also have a specific high specific energy, okay, but sometimes it is shown that the electronic conductivity is not good. Then people did research on hybrid electrolyte. So, there are several electrolytes which have been studied, and one can find a detailed literature on electrolyte, and it is important to know. Okay. So, we are not going to discuss much more about electrolyte, but one can find it in the literature what are different electrolytes and how they are being used in lithium ion battery. So, now we come to the point of what are the applications of lithium ion battery. Okay. There are a lot of applications in lithium ion battery. Okay. Most of the portable electronic devices nowadays people carry there are lithium ion batteries, and apart from that also like pacemaker, there are lithium ion battery, digital cameras, lithium ion battery, PDAs or personal digital assistants, smartphone, laptop, watches, everywhere there are lithium ion batteries. You can see that these are the lithium ion batteries which they look like. If you open it, you will find this type of batteries. Okay. So, why these batteries are used? There are a typical reason like durability. Durability is a very important thing, because when you use lithium ion in pacemaker, one has to make sure that the capacity should last for long time. So, durability should be very good and should be very lightweight. Typically, these lithium ion cells are very lightweight of few grams. Okay. Therefore, they are good for pacemakers. Okay. And then they have high energy densities, okay, and lighter than other type of batteries. That is what just now I discussed, and charging is easier, okay, and next is maintenance is at low cost. All right. So, these are typical the properties or qualities of a lithium ion battery, which actually these days which actually in the market people use lithium ion battery for so many portable electronic device application. Okay. But the question is how much safe they are. What are the safety issues? We do use, but are they safe? Okay. So, you can see that one laptop which is getting burnt using lithium ion battery. Why? The reason behind this is that, as I discussed, the lithium ion battery, it is basically the transport of lithium or shuttling of lithium between anode and cathode, okay, by intercalation and de-intercalation process. Alright, because of this movement of the ion, there is a heat generation. Alright, but this is a natural process, heat will be generated. Whatever battery you use, you will find there is a heat. When you use a laptop, when you use anything which is driven by battery, if you charge it for some long time, you will touch it and you will find, or if you use it for long time, you will find that the device get heated. Okay. But one should have a good way to dissipate this heat. So, in lithium ion batteries also one needs a very good dissipation of heat. So, safety is a very important concern for lithium ion battery like other battery. So, therefore, one needs to know few important things which are good for these the safety issues. One is the battery chemistry, one is to know that, one is to know about the operating environment. Okay. If the operating environment keeps on changing, okay. Suppose you use a laptop, you use it now in an environment and then you again take it to environment which is very hot, then definitely the operating environment changes and there could be a possibility of thermal runaway of this device, and then you end up with this type of destruction of the device. So, one is to be very careful about the operative environment, and then the tolerance is a very important thing. What is the tolerance of any device at a particular environment or at a given the structure of the device, what is the tolerance, and then the instability. So, there could be mechanical instability, thermal instability, electrochemical instability, etc. So, let me just summarize today what we have discussed. So, I continued my discussion on electrode material for lithium ion battery. Okay, so, we have seen what are the different bulk material which are appropriate material for cathode, anode, and what are the reasons for using these materials. Okay, as far as the cathode is concerned, I discussed about say LCO or NMO or NCM. These are the materials used for cathode, or spinel oxide or polyanion for anode. We have seen carbon based material, graphite, CTM. Okay. These are typical material for anode. And then we address the issue, then when we go from bulk material to nanomaterial, what are the advantages we see in terms of the performance of the electrodes. Okay. And we discussed different nanomaterials, different nanomorphology as anode, different nanomorphology at cathode. So, we have also made a comparison. Suppose we have a nanoparticulate system, we go to nanorod system, we go to a particle system, but with some sort of coating. So, these are all morphologies or a branched morphology. Okay. So, these are all morphologies which people have worked with, and we have addressed those morphology and how they influence the performance. Then we discussed what the electrolyte in lithium ion battery, what is important, what are the type of electrolytes used in lithium ion battery, and what are the typical properties that one should have when we use one electrolyte for lithium ion battery. I have also discussed about applications of lithium ion battery, and finally, we have seen what are the safety issues in lithium ion battery and what is the need to make a very safe environment when one works with a lithium ion battery for different devices. Okay. Thank you.